So combining the data from Lucy, Psyche, and Earth-based telescopes, scientists are hoping to better understand both the three-dimensional structure of the comet and the nature of the dust. It's a rare opportunity to compare ancient dust from a distant solar system to that from our own. At the beginning of October, 3I Atlas passed within 20 million miles of Mars, which gave our Mars spacecraft an opportunity for a close-up. This picture is not a direct picture of the comet itself. It's a spectrum. The spectrograph, the ultraviolet spectrograph on MAVEN, has looked at the comet and also split up the ultraviolet light according to color. So you're seeing three different bands in this image. On the right, you're seeing emission from hydrogen gas in the atmosphere of Mars. In the middle, there's a fainter band indicating that's coming from hydrogen gas in interplanetary space. And on the left, that blob is the signature of hydrogen gas coming from comet 3I Atlas. It's a little blob rather than a big streak because the comet is a small object in the sky relative to great big gigantic Mars and interstellar space that fills the entire field of the instrument. This image highlights the value of spacecraft and instruments designed to look directly toward the sun, not only to study the sun, but also to have the ability to see other objects crossing, in this case, behind the sun from the telescope's point of view. NASA's Psyche mission acquired 4 broadband black and white images of the comet over the course of 8 hours on September 8th and 9th, 2025. The comet was about 33 million miles from the spacecraft at that time, and you can see in the image the large frame where the comet was seen at different times. Down in the bottom left is a blow-up, a stack in addition of all of those observations. Lucy was 240 million miles away from 3I Atlas, which is circled in the center, when its high-resolution LaLaurie camera caught the comet. You can see the comet's coma, the fuzzy halo of gas and dust surrounding 3I Atlas, and its tail, a smudge extending to the right of the comet. If you were the Lucy spacecraft looking at the comet from this angle, the sun would be a little bit over your left shoulder, and so the comet tail is pointing away from the sun, as we've seen many times before in solar system comets.
In this case, our astrophysics missions came together to take advantage of this rare opportunity to study this comet that came to us from outside the solar system. At this point, 3I Atlas was about 277 million miles from Earth. And what Hubble's images revealed was a few things. First, a teardrop-shaped coma of dust coming off that solid, icy nucleus of the comet itself. Astronomers were able to more accurately narrow a few things. Importantly, the size of the nucleus. We now know it's between, at that point actually, we knew it was between 1,400 feet in diameter up to as large as 3.5 miles in diameter. And Hubble also saw that the comet was losing dust. And not just losing it, but losing it at a rate consistent with other previous sun-bound comets that originated from within our solar system. We detected an abundance of carbon dioxide gas in the comet's coma and in the bright cloud of gas and dust surrounding that comet as it approaches the sun. We now know from seeing those science wiggles, those fingerprints of those molecules, that the comet has a nucleus rich in carbon dioxide as well as the presence of water ice. Now, the ratio, like we can not just say that these things are there, we can also say, what's the ratio of carbon dioxide to water? And we now know that. We know it's larger than what we usually see in solar system objects. But there's a lot of natural explanations for that. For one, the carbon dioxide is going to kind of bake off that comet earlier on when it's far away. But there's other well-understood processes that could also explain it. I'll just, to put this in context, there are, every time we look beyond our solar system and we look at the ratios of carbon dioxide to water, we see, whether it's a star or a planet, different ratios than we see in the solar system, and that's true for this comet as well. So it could mean, and this is the last theory of why those ratios could be different, that these ices could have been exposed to higher levels of radiation than comets in our own system. Or, as I said before, could be that the comet just formed from a region where carbon dioxide ice was particularly abundant and different from our solar system.